welcome back. In my last video, we learned how to take implicit derivatives. That is, we learned how to take the derivative of equations where you can't get y by itself, where your variables are sort of mashed together and can't be separated. Today, we're going to get more practice with implicit derivatives and look at a couple different kinds of problems that we didn't see in the last video. Starting with example 1, write the equation of the line or lines tangent to the curve y squared minus xy equals x plus 5 at the point where x equals 1. So I see equation of the tangent line, boom, I'm thinking point slope. So to find the point, I'm going to take x equals 1 and plug it into this implicit equation. So when I plug in 1 for x, I get y squared minus y equals 6. And already I noticed that if I try and solve this for y, because it's quadratic, I'm probably going to get two solutions. So I get y squared minus y minus 6 equals 0. That factors into y minus 3 times y plus 2. So my solutions are y equals -2 and y equals 3. What does that mean? It means that this graph actually has two different points when x is 1. It goes through the point 1, -2 and through the point 1, 3. So 2 points means two tangent lines. But first I have to find the derivative. So to take the derivative of this implicitly, I'm going to take the derivative of y squared, which would be 2y, times dy dx, because I'm taking the derivative with respect to x, minus the derivative of xy. This requires the product rule. We saw this in the last video. The derivative of x times y is y plus x dy dx equals 1 plus 0. So I need to get dy dx by itself, so I have to plug in multiple different points here. So 2y times dy dx minus y minus x dy dx equals 1. Keep all my dy dx's on the same side, send everything else away, giving me 2y dy dx minus x dy dx equals y plus 1. And now I know my next two steps are factor out dy dx and then take everything else and divide it away. So I can already see that my answer, dy dx, is going to be y plus 1 divided by 2y minus x. So now that I have my derivative, I can plug in my points. So dy dx evaluated at the point 1, -2 is going to be -2 plus 1, which is -1, divided by -4 minus 1. So -1 over -5 is 1/5. So my point, 1, -2, has a slope 1/5. So using point slope form, y minus -2 equals 1/5 times x minus 1. And for my other point, dy dx evaluated at the point 1, 3 is 3 plus 1, 4, over 6 minus 1, so 4/5. So for this point, y minus 3 equals 4/5 times x minus 1. So be aware, when you're finding the equation of a tangent line, but it's an implicit equation, you might have 2 points, which means you might have 2 lines. So be on the lookout for that. So in my second example, this symbol right here, d squared y over dx squared, means take the second derivative. Specifically, it means take the second derivative of y with respect to x. So I need to take two derivatives of x squared plus y squared equals 100, which you might notice is the equation of a circle centered at the origin with a radius of 10. So to take the first derivative implicitly, I'm going to get 2x plus 2y dy dx equals 0. To get dy dx by itself, I'm going to subtract the 2x and then divide by 2y. So dy dx equals -2x divided by 2y, which is -x over y. So that's my first derivative, dy dx equals -x over y. To find my second derivative, I'm going to take the derivative of -x over y, which is going to require the quotient rule. So my second derivative, d squared y over dx squared, equals, using the quotient rule, the derivative of the top, -1 times y, minus -x times the derivative of y, which is dy dx, over y squared. And you might be tempted to box and run right here, but we're not quite ready for that, because dy dx, I already have an expression for dy dx. I know dy dx equals -x over y. So when you take a second derivative implicitly, you're usually going to have this step where you need to substitute dy dx back in. I'm going to substitute -x over y in where it says dy dx. So this gives me -y plus x times negative x over y squared. You can certainly box and run right here, but it's not too hard to clear this complex fraction by multiplying the numerator and the denominator by y, giving me negative y squared minus x squared over y cubed. So both of these answers are good. Next up, we got another second derivative problem, so feel free to pause the video and practice this one on your own to see if you can get the right answer. Just as a hint, on the right-hand side where you see 2 times x times y, you're going to need to use the product rule there. It's going to be much easier if you treat this as 2x times y. Okay, so let's find the first derivative. The derivative of 3y is 3 dy dx plus 0 equals the derivative of 2x times y. So that's going to be, using the product rule, 2y plus 2x dy dx. Getting dy dx by itself gives me dy dx equals 2y divided by 3 minus 2x. Now that I have dy dx, using the quotient rule, I'm going to take the derivative of this. So the second derivative, d squared y over dx squared, is going to be 2 dy dx times 3 minus 2x minus 2y times the derivative of 3 minus 2x, which is negative 2, over 3 minus 2x squared. And just like in the last problem, I'm going to substitute. I need this dy dx. I'm going to plug in 2y over 3 minus 2x. So this gives me 2 times 2y over 3 minus 2x. I'm just going to write 4y over 3 minus 2x times 3 minus 2x plus 4y over 3 minus 2x squared. And while you could box and run right here, what I immediately notice is that this 3 minus 2x and this 3 minus 2x are going to cancel each other out, leaving me with 4y plus 4y in the numerator. So I've got 8y divided by 3 minus 2x squared. And I like that answer. All right, 2008 AB number 25. If x squared y minus 3x equals y cubed minus 3, then at the point negative 1 comma 2, dy dx equals what? Well, I can look at this and I immediately recognize that it's an implicit derivative because I couldn't get y by itself. So I'm going to take the derivative implicitly, and I notice going in that I'm going to have to use the product rule on x squared y. So here we go. The derivative of x squared is 2x times y plus x squared times dy dx minus 3 equals 3y squared dy dx minus 0. So I've taken the derivative implicitly. Now I have two options. I can get dy dx by itself, then plug in negative 1 comma 2, or I can just plug in negative 1 comma 2 right now and then get dy dx by itself. Both will work, but I'll tell you, I tend to prefer plugging in the point now because I think you do less work in the long run. So I'm going to plug in negative 1 comma 2, so 2 times negative 1 times 2 is negative 4, plus negative 1 squared, 1 dy dx, minus 3 equals 3 times 2 squared, 3 times 4 is 12 dy dx. And now I'm just going to solve this equation treating dy dx like a variable. So on the left-hand side, negative 4 minus 3 is negative 7, and I'm going to subtract the dy dx over to the right-hand side, giving me 11 dy dx. And then just divide by 11. So dy dx equals negative 7 over 11, and my answer is A. And 2012 AB number 27, if x plus 2y times dy dx equals 2x minus y, what's the value of the second derivative at the point 3 comma 0? So they're asking for the second derivative, but they already gave me the first derivative, right? It's not too much work to simply divide that term over. So dy dx equals 2x minus y divided by x plus 2y. So I have dy dx, now I just need to take a derivative of that to get my second derivative. So my second derivative, using the quotient rule, is going to be the derivative of 2x minus y, which is 2 minus dy dx, times the bottom, x plus 2y, minus the top, 2x minus y, times the derivative of the bottom, which is 1 plus 2 dy dx, over the bottom squared, over x plus 2y squared. Now here's a hint. Instead of plugging in dy dx and trying to substitute in that term before I do all the plugging in, this is going to get really messy. So instead, I'm going to plug the point 3 comma 0 into dy dx. dy dx evaluated at the point 3, 0 would be 6 minus 0 over 3 plus 0, so it's 2. And what that allows me to do when I plug in the point 3, 0 to this big quotient rule is everywhere I see a dy dx, I know I can just substitute in a 2. And that's going to save me just a little bit of time and effort here. So the second derivative evaluated at the point 3, 0 is going to be 2 minus 2 times 3 plus 0 minus 6 minus 0 times 1 plus 4 over 3 plus 0 squared. That's going to give me 0 times 3 is 0, minus 6 times 5 is 30 over 9. Negative 30 over 9 reduces to negative 10 over 3. And again, my answer is A. So to recap, not a lot of new material today. We're still taking derivatives implicitly, but we did learn that if you're trying to find the equation of a tangent line, be on the lookout for multiple points, which means multiple tangent lines. And we learned how to take a second derivative implicitly. We just have to remember to plug in the dy dx when you take the second derivative. Make sure and get lots of practice with implicit derivatives, because what we're doing next, related rates, is something that beginning calculus students often think is very difficult. But if you have a solid foundation in implicit derivatives, it's not as hard as it would be. So get the practice now. It's going to help you tomorrow. All right, I hope that helps. Thanks for watching.